This is my presentation on the linear probability model. So what the linear probability model ultimately is a unique version of the binomial regression, which means that it can either return a 1 or a 0 as its component. So going off of this, it compiles these ones and zeros in unique individual events to compile a larger model. So this is excellent for when your response variable is continuous. So it could be weight or height or number of hours something takes to cook, for example. So using these numerous outcomes, we establish a relationship between the independent and dependent variables. So we use this relationship to predict changes in a dependent variable for incoming variables, if that makes sense. So we use the ordinary least squares method to minimize the errors of the zeros and ones and find a line of best fit based on the number of ones and zeros that we return in our model. Continuing on from the linear probability model, I'd be remiss not to speak on the logistic model. As we discussed, the linear model used is when your response variable is continuous, as we talked about weight, height, or number of hours cooked. But when your response variable is not continuous, we use the logistic regression, and this is when it's categorical in nature. For example, maybe it is yes or no, true or false, or a color, for example. The logistic regression uses the maximum likelihood method to arrive at the solution, which contrasts from the linear probability model, which uses the ordinary least squares. So continuing off the comparison, I want to get back more in depth on the linear probability model. So the linear probability model is excellent for determining the probability that an event will have a binary return. So as you can see from this picture, the line will give us a probability of whether or not our return value will be a yes or a no. Now this is awesome, except as you can see from the graph, on the corners of the graph, the tails, we get a possibility of a return of less than 0 or greater than 1. This essentially means that our expected value is more than 100% likely to happen or less than 0% likely to happen. This is a weakness of the linear probability model because these are obviously impossible ideas. However, within the 0 and 1 brackets there, the linear probability model is excellent for determining our outcomes. So to conclude this presentation on the linear probability model, it is a super useful model. However, in many instances, it's wrong. As we discussed at the tails of its graphs, the return values simply do not make sense. However, as a statistician, using this probability model with a common sense mindset, it can be as useful as any model